In real life, we have seen a lot of queues, but how do we model them? In general, for any queue, we can separate the process into customer arrivals, and then the company will provide some service to the customers. And after the service, the customers will leave the queue and the cycle repeats. Let's first focus on the first part, customer arrivals. To model the customer arrivals, we make an important assumption. The arrival times are independent from each other. And by independent arrivals, I mean that a customer arriving at a specific time has no knowledge about the other customers nor their arrival times, sort of showing up at random. Practically, you can think about it like this. On the timeline, we can divide it into many subintervals. At each subinterval, it is kind of like flipping a coin, and with some certain small probability p, there is a customer coming into the queue. If we divided one unit of time into n subintervals, and at each interval there is a probability p that a new customer shows up, then on average, we should expect there to be n times p number of customers coming in one unit of time. However, ultimately we would like to let n tend to infinity rather than having discrete intervals. To make sure that we don't end up with infinite number of customers turning up, we adjust the probability p to change with the number of intervals, lambda over n, so that on average, within one unit of time, we get lambda customers coming in, and that lambda is a constant. And once we have set this up, we can analyze this as a usual probability problem. One possible thing we might be interested in is the probability that there are k customers coming in during this time. Each customer arrival would contribute lambda over n probability, so there would be lambda over n to the k probability in those intervals, but for all the other intervals to not have customers coming in, we would have to multiply 1 minus lambda over n minus k times. There could very well be other sets of intervals those k customers come in, so we also have to multiply an extra n choose k factor to include all possible ways customers could come in. So this is the formula for the probability of k customers coming in within this time. Ultimately, we would like to subdivide it into many more intervals, letting n to infinity. So we just have to evaluate this expression when n tends to infinity. And this is the final expression that we get. This was originally the probability of getting k customers coming in if on average we expect the number to be lambda. So for a summary, if we have an average rate of lambda customers coming in, the probability that there are exactly k of them in a unit time interval is this exponential expression, which can be put in the form of a table, making it a little bit more obvious that we can view it as a distribution of the number of customers. Such a distribution is called Poisson distribution, and the entire model of customer arrivals is called the Poisson process. So we have modeled the customer's arrivals by the Poisson process, but that's just part of the queuing model. we also have to incorporate the service part of the queue. The model I will describe is quite unrealistic, but mathematically the simplest to work with. I will describe other models at the end. For the arrival process, there is a lambda over n chance of a customer coming in. We assume that at the same time, the departure process, that is, the service is finished for a customer, also happens independently with the same mechanism, just with a potentially different constant, mu. Of course, that is when there is at least one customer in the system, otherwise no departure can happen. This is quite an unrealistic model because the duration of the service is completely determined by luck. But putting both arrival and departure in the same framework simplifies a lot. Usually, we like to represent this process in a more compact way. We denote the state of the queue by how many customers there are in the system. For example, state 0 means no customers in the queue and the queue is clear. The customer arrives at a rate of lambda, so it advances from state 0 to state 1 at a rate of lambda, and so on for the other states. At the same time, by our rather unrealistic model, the customers leave at a rate of mu, so the rate at which the number of customers go down 1 is mu. At the start of this queuing process, we would assume that we don't have any customers. In other words, initially, the probability of the state being 0 is 1, but for the other states, initially the probability is 0. In general, these probabilities will evolve over time, with the probabilities denoted as pk of t, where that k is the state of the queue. These values above are just the probabilities when t equals 0. One possible direction for analysis of this queue is to study the evolution of these probabilities. For example, let's focus on the to state and the neighboring states. What happens if we just move time forward by 1 over n, one subinterval of time? There are 3 contributions to this probability. First case is that at time t, it was at state 2 already, but no customers have arrived or departed during that tiny time interval. The contribution looks something like this. P2 of t denotes the probability that at the time t, it was actually at state 2, and the other part is the probability that neither arrival nor departure happens within the time between t and t plus 1 over n. 1 minus lambda over n is the probability of no arrival, and 1 minus mu over n is the probability that no customers have left the queue this time. This is only one of the possibilities, not changing the state of the queue. The second possibility is that at time t, the queue was at state 3, but a customer left after the service. This case contributes this term on the right. Like before, P3 of t is the probability at state 3 at the previous step, and mu over n is the probability that a departure happens during this time. The final possibility is that originally it was at state 1, and then a customer comes in during this time. The contribution would be P1 of t, the probability that originally it was at state 1, times lambda over n, the probability that an arrival occurs. So this expression on the right is how P2 evolves as we increment one subinterval of 1 over n. But this is just focusing on the evolution of P2. The exact same argument would apply for any state k, so we should expect a similar equation for state k. I have literally just replaced any instance of 2 to be k, 3 to be k plus 1, and 1 to be k minus 1. This equation works almost all the time except for the case when k equals 0, because we can't have -1 customer in the queue, so this term doesn't make sense. No worries, it just means that we need to deal with the case k equals 0 separately, and the process is very, very similar to what we just did. To contribute to the probability at state 0 at time t plus 1 over n, we can either not lucky enough to get a customer arrival, in which case the contribution is probability that you were originally at state 0, times 1 minus lambda over n, the probability that you haven't got an arrival during this time. Or, there was originally 1 customer in the queue, and during this time, the service has finished and the customer left the queue. The contribution in this case would be P1 of t times mu over n, the probability of customer departure during this time. So we have completed the derivation of these evolution equations from time t to time t plus 1 over n, with the first equation working for almost all k, except for k equals 0, and the second equation specifically dealing with the case k equals 0. As with previous discussions, we would like to let n tend to infinity so that we are no longer using discrete time intervals. Let's focus on the first equation first and think about what happens when n tends to infinity. The first step is to rewrite the left-hand side so that it becomes like a rate of change. For the first term, we subtract pk of t from it, and then multiply the term by n, giving us pk of t times negative lambda minus mu plus lambda times mu over n. And for all the other terms, we just have to multiply by n. Finally, we just have to consider the limit of all these as n tends to infinity. The left-hand side would tend to the derivative of pk of t. The first term on the right-hand side would tend to negative of lambda plus mu times pk of t, and the remaining 2 terms do not depend on n, so they tend to whatever they were before. This becomes a differential equation in the continuous case, but this again only works when k does not equal to 0. We just now have to deal with the case when k equals 0. This comes from considering the limit of the second equation when n tends to infinity. In very much the same fashion, we consider the rate of change of p0 of t. We subtract the first term by p0 of t, and then multiply it by n, giving us negative lambda times p0 of t. For the other term on the right-hand side, we just multiply it by n, giving us mu times p1 of t. Again, the left-hand side would tend to a derivative, in this case p0 prime of t, and the terms on the right-hand side do not depend on n, so they tend to whatever they were before. This would be the differential equation coming from the case for the state 0. So altogether, we would have these differential equations governing the evolution of these probabilities. In theory, we could just solve them and pretty much everything you want to know from this queuing model falls out. However, even in this rather simple queuing model, the exact solution looks horrible. And not only is it horrible, these IKs or ILs are actually special functions called the modified Bessel functions of the first kind. To be fair, these Bessel functions are hugely important in many different fields, including Schrödinger's equation, so it is not really obscure and a lot of properties are known. Still, due to the complexity of the exact solution, we might be better off analyzing more qualitative behavior. For example, what is the long-term behavior of these probabilities? If we assume that the system becomes stable in the long term, which means that these probabilities eventually tend to a constant for each k, what are those pi k's? Well, using this assumption and plugging it back to the differential equations, in the long run, these derivatives vanish and all the other pk of t's can be replaced by the constants pi k. Then, we end up with a recurrence relation between these pi k's. Solving this is much easier than the full differential equations, and this is what we will do. To start with, we can rewrite the first recurrence relation as such. This highlights that the difference between consecutive pi k's is related by a ratio of lambda over mu. What this means is that if we have the value of pi 1 minus pi naught, by multiplying lambda over mu, we get the next difference, pi 2 minus pi 1, and so on by multiplying lambda over mu all the way through. Making our notations a little easier, we write the initial difference to be d, then the other of these differences would be a power of lambda over mu times d. Now, for example, if we know the value of pi naught, then we can obtain the value pi 4 simply by adding up pi naught and these differences. The sum telescopes to pi 4. Now, because we can rewrite these differences in terms of lambda over mu and d, in general, we have that pi k is the sum pi naught and the sum of these differences between consecutive terms, which are powers of lambda over mu multiplied by d. So that's the conclusion we draw from the recurrence relation. But the other equation from the long-term behavior of these probabilities involves pi naught and pi 1. This tells us that pi 1 is this lambda over mu times pi naught, which means that the difference is this lambda over mu minus 1 times the initial pi naught. Because we have denoted the difference as d, we just have to substitute this formula for d into the previous expression for pi k, giving pi k in terms of pi naught and lambda over mu only. Now notice that this part is actually a factorization of lambda over mu to the k minus 1, and using this observation, we can conclude that pi k are actually just a multiple of pi naught and a power of lambda over mu. So during this quest of finding the long-term behavior of these probabilities, solving these recurrence relations means that the long-term probabilities should look like these at different states. Like at state 3, if the probabilities stabilize, then it must be pi naught times lambda over mu cubed, and so on. Finally, to fully solve this system, we actually have a bit of a hidden assumption, as these indicate probabilities. That is, the sum of these probabilities has to be 1. Given that these probabilities form a geometric sequence, we can compute the sum of these probabilities by the formula for a geometric series if it converges and get that pi naught over 1 minus lambda over mu equals 1, which in turn means that pi naught is 1 minus lambda over mu. However, note that this geometric series only works if it converges. That is, the ratio lambda over mu is smaller than 1. Well, to be honest, just looking at pi naught, we also know that lambda over mu must be smaller than 1 for this argument to make sense. And this condition, that lambda needs to be smaller than mu makes sense. If instead lambda is larger than mu, then on average, lambda being the average rate at which the customer comes in, is quicker than mu, the average rate that customers are being served. So the general direction would be towards more and more customers in the queue, and it becomes less and less likely the queue would ever clear. Because there will be more and more people in the queue, this queue does not stabilize. On the other hand, if lambda over mu is smaller than 1, then the general direction is flipped, and this means that if any customers decide to show up, they will be served quickly. In this case, everything would be under control, and even if the queue is still dynamic, the probabilities stabilize. More specifically, in this case, if you just randomly take a look into the queue, these are the probabilities that you find the queue in these states in the long run. And the probabilities wouldn't change even if you wait longer. Compared with the case where the general direction is going towards more and more customers in the queue, let's say at some point in time, the queue is most likely in state 2, then because the general direction is drifting towards more customers, at some point, the queue is most likely in state 3 and so on. So in this case, the probabilities shift and don't stabilize. In the case where the probabilities do stabilize, this is called the invariant distribution, the long-term limit of the probabilities. Now, of course, this queuing model, as I said, is quite unrealistic because the service times have a very bizarre property, which is that whether you start your service at this time or this later time, there is no impact on the remaining service time. In other words, the service time does not care about its history. Regardless of whether you start the service earlier or later, there is always a probability of mu over n that the service will be completed within a time interval of 1 over n. Such a property of service times is called memoryless. Well, actually the arrival process is also memoryless in this model. Regardless of whether the previous customer arrives early or not, there is always the probability of lambda over n the next customer arrives within the next small time interval. And this is why the process I've described so far is called an MM1 queue. The first M stands for the arrival process being memoryless, and the second M stands for the service times being memoryless. 1 here stands for there only being one service counter. But of course, we can have an MMC queuing model, so the people would still queue up, but there are more than one counters to serve those customers. So the customers still come in at a rate of lambda, but in total, the rate of service would have been much faster than just one service counter. Actually, we can generalize this even further to an MGK queue, where there would be K counters, and G here stands for general, so the service times might not be memoryless anymore and follow a general arbitrary distribution. We can make this even more general by considering a network of queues. The simplest so-called Jackson network is to consider multiple individual MM1 queues, but they interact with each other in the sense that after the service, the customer could leave the system entirely or join the back of another queue in this network. Needless to say, these are more complicated than normal MM1 queues. However, because even for the simplest MM1 queue, we have a rather complicated full solution, we might be more interested in the qualitative behaviors, like the invariant distribution and the long-term behavior instead. What is shown here is only a glimpse into the field of queuing theory, the art of modeling real-life queues. However, For the next video, we will need an extra bit of information on Poisson distribution, which I have made another video for it on the second channel, and you can click on the top right corner for it. If you enjoyed this video, please like and subscribe with notifications on and leave a comment, and don't forget to check out the video on the second channel before my next video. Bye!